Good morning, one and all. So, in the last class, we have started discussing about BPSK and its transmitter and how to find the probability of error. Now, this is the basic formulas to find out the probability of error of any modulation scheme. What is that? 1 by m summation I equal to 1 to m probability that x does not lie inside ZA given mi cent, or this can be written as 1 minus 1 by m summation I equal to 1 to m probability that x lies inside ZA given mi cent. Now this is how we write this formula. What do we do here? We replace this conditional probability with area under conditional PDF. Why? Because you know already probability means area under PDF. Now this is the constellation of the BPSK, which is a one-dimensional figure having only one basis function, and these are 2 points, and this is the threshold, that is 0. Now we have divided this region into two separate regions, namely Z1, Z2. Z1 is from 0 to infinity, this is from 0 to minus infinity. Now what is the distance between these two message points? How much is that? D12, that is 2 times root of EB. 2 times root of EB, that is a distance between message point 1 and message point 2. Okay. Now these are the transmitted signals of BPSK for symbol 1 and for symbol 0. Now they are negative of each other. So one is independent, one is dependent. That's why we need only one basis function. Now this is the ML rule for the BPSK where threshold is 0. So what is ML rule says? If the received vector x lies in region Z1, what do you decode? You decode as a symbol 1, or you estimate that symbol 1 is transmitted. If it lies in region Z2, what do you say? You say that symbol 0 is transmitted. That is your estimation. Okay. Now if it lies exactly on this boundary, so we take a random guess. By taking random guess, we say that either symbol 1 is transmitted or symbol 0 is transmitted. Okay. Now this is the receiver. As I told you already, it has got two subsystems, namely detector or demodulator and the decoder. This is ML decoder. This is the correlator, which will act as a detector or demodulator. So there is only one correlator because it has got n equal to 1. If n equal to 2, you get two correlators. So in general, you have a bank of n correlators. This is the receiver. It is called coherent receiver. Why coherent? So in the transmitter also, we are using a basis function. Where is the transmitter? So if you remember properly, so the transmitter part also, to try to remember it later. The transmitter also we are using same basis function. In the receiver also we are using the same basis function. So there is a coherence in the phase, in the frequency, in the amplitude of the basis functions that we are using in the transmitter and the receiver. Just like a carrier coherence. That's what it's called, a coherent receiver. Okay. Now, so you know that m equal to n equal to 1. That's why x equal to x1. So x is not a vector now. It is simply point because n equal to 1. Now, so what is fx of x given mi? This is what the generalized conditional PDF of capital X given mi. We have found out this. We found out. So the conditional PDF of capital X equal to product of conditional PDFs of individual elements of the vector capital X. I told you all these things in the previous classes. So if you have any doubts, please refer those classes. But here I equal to 1 to 2. M equal to 2, no? I varies from 1 to 2, but n equal to 1. So this n equal to 1. M equal to 2, n equal to 1. Substitute here. So 1 means fx of x given mi pi n whole power minus 1 by 2 expectation of exp 1 by minus 1 by n naught x1 minus si1 whole square. I equal to 1 to 2. If I equal to 1, m1, what the first symbol? 1. m1 equal to 1. fx of x given 1 equal to, this is what is expression. fx of x given 0 equal to, this is expression. Now these are the two conditional PDFs of x given 1, x given 0. Here what is x? It is nothing but x1 only. Okay, no need to mention each and every time. Here, so the received vector or observation vector is also a point. What is the point? x1. Okay, so here we don't have any vectors actually. So there is no signal vector, there is no received vector. So the vector become only points. Why? Because n equal to 1. Okay. Now this is very important thing you must remember. So these are the two conditional PDF of vector capital X given symbol 1 is transmitted, and this is for vector capital X given that when symbol 0 is transmitted. These are two conditional PDFs we have. But let me tell you what is S11, what is S21, what is S11. This is root EB. What is S21? Minus root EB. You can substitute here. So S11 is root EB, S21 is minus root EB. Is it so? Right. So substitute those two values also, and this is the complete conditional PDFs. We have two conditional PDFs. Why? Because we are transmitting two symbols. So for symbol 1, for symbol 0. Now let us find out the probability of error of BPSK. Now till now I told you the generalized procedure to find out the probability of error. What is the procedure? This is what is procedure, final procedure. 1 by m, summation I equal to 1 to m, probability that x does not lie inside Zi given mi cent. This is what the formula is, or this formula. You can use either of these formulas. So here I will use this formula. Why? I will tell you the reason. So what is the formula I am using? So this formula, probability of error equal to 1 by m, summation I equal to 1 to m, probability that x does not lie inside Zi given mi cent. But here m equal to 2. So m equal to 2 means we have two regions, Z1, Z2. Okay. Now what happens? 1 by 2, probability that x does not lie inside Z1 given 1 cent plus probability that x does not lie inside Z2 given 0 cent. Okay. Now, so here, so we are using a little trick here. So I can further simplify here. It is, let me tell you, let me go back to the constellation diagram here. So what I want to say is, if x does not lie inside Z1 means it lies in Z2, because we got only two regions. So if there are only two regions, if x does not lie inside Z1 means obviously it lies in Z2. Similarly, if x does not lie inside Z2 means where does it lie? It lies in Z1, isn't it? Okay. So because we don't have so many regions, we have only two regions. Okay. Now that's why. So this can be further written as x does not lie inside Z1 means it lies in Z2. As simple as that. In the same way, if x does not lie inside Z2 means it lies in Z1. Okay. Now finally I can conclude by saying like this. This is what the probability of error. See, so it is happening only in the case of BPSK because we are having only two regions. Okay. If there are more than two regions, we cannot write like this. Okay. But here we have a luxury or we have a flexibility of writing like this. So we are writing. So we are using that flexibility to simplify our calculations. Okay. So I hope you appreciate this point. Okay. So just look at this point and you will understand very clearly. This is what the final formula. Now, but we have to find out these probabilities. This probability and this probability. You know already what the probability means, area under PDF. Now this is a conditional probability. Obviously, it would be equal to area under conditional PDF. Okay. Now I am finding this probability. So here, what probability I want? Probability that x lies inside Z1 given 0 cent, which means I am finding the area under what PDF? Fx of x given 0. Integration over what region? Z1. Isn't it? Now, so what is Z1? What is Z1 region? From where to where? 0 to infinity. So I am substituting Z1 where from 0 to infinity. It is one dimensional, no? 0 to infinity. Fx of x given 0 dx. Now what is fx of x given 0? This is the formula, this expression. Here what is S21? Minus root AB. So you substitute everything here. What do you get here? This is the formula. S21 is minus root AB. This is what you get. Finally, this is the integral. You need to simplify. What is that? 1 by root pi n naught integration 0 to infinity e power minus 1 by n naught into x1 plus root EB whole square by dx1. So please remember, I am writing x as x1. X becomes x1 only. Why? Because n equal to 1. So I told you all thing. X equal to x1. Only one point is there. In the vector there is only one point is there. Okay. Now, so we have to simplify this standard expression. So I am writing z equal to x1 plus root eb by root n naught. What I am writing here is x1 plus root eb by root n naught as some z, some other variable. Now this is the limit of integration. So finally it becomes like this. So you go through this simple integrals. So I am just altering or writing integrals in the convenient form. Now this is what you get finally. Okay. So I just done some simple calculations. Okay. I hope you appreciate this point. You just go through these simple calculations which I have done now itself. Okay. So before that, so let me go to some of the important topics which we have discussed in case of PTSP course also. So there is something called Q function. I told you there itself. It is very, very important. What is standard formula? Q of x equal to 1 by root 2 pi integration x to infinity e power minus z square by 2 dz. Okay. So there is one more one, that is error function. How it is defined? 2 by root pi integration 0 to x e power minus z square dz. There is one more function, ERFC. It is called complementary error function. What is called? Complementary error function. How it is defined? 1 minus error function. How it is defined? So 1 minus of this. So 2 by root pi. So 0 to x, it becomes x to infinity e power minus z square dz. Okay. So these are the relation between a Q function and the complementary error function, ERFC. It is very, very, very important. Okay. So please remember, we always express the probability of error either in the Q function format or either in the complementary error function format. Okay. So mostly we express it is in the form of Q function, or sometimes we may express in the form of ERFC, complementary error function. You must know these two. Otherwise you can do like this. You remember expression in the Q function format, and you can find, if you remember this relation, you can transform into another format. Okay. Because this is a relation between ERFC and Q function. If you know the expression in the one format, you can convert it into the other format. I hope you are okay with this point. Okay. So this is very, very important. You must remember this. Everything is very, very important. Okay. Now what is ERFC of x? 2 by root pi integration x to infinity e power minus z square dz. You compare this with this one. 1 by root pi root eb by n naught to infinity e power minus z square dz. Okay. So if you do some simple calculations, you get something like that. It is equal to, what is equal to? Of ERFC of root of eb by n naught. You compare with this expression. 2 by root pi, here what is missing? 2 is missing. That's why I am writing 1 by 2. So what is there here? Here x to infinity, that's why I am writing ERFC of x. Isn't it? So here what is the lower limit of integration? X. Upper limit infinity. So what is this? ERFC of x. ERFC of x is the lower limit of integral. Correct? Here what is the lower limit of integral? Root eb by n naught. That's why I am writing root eb by n naught. Now what is this? Probability that x lies in z1 given 0 cent. Okay. So it is a one probability. What do you mean by that? X lies in z1 given 0 cent, which means, so x lies in z1, but what is cent? 0 cent. So what do you mean by this? Okay. Actually we are transmitted 0. Okay. But x lies in z1, we are decoding as what? If x lies in z1, how we decode? We decode as 1. This is error. Okay. So actually it is given that 0 is transmitted. But so since the received vector is lying inside region z1, we are estimating it as symbol 1. Now we have gone wrong. Actually the transmitted symbol is 0, but we are decoding it as 1. That is one type of error. What is other error? We may transmit 1, but we may decode as 0 at the end of the receiver. Okay, since it is symmetric, so the probability of 0 becoming 1 is same as 1 becoming 0, because everything is same, isn't it? So this is Z1, this is Z2. It is 0 to infinity, it is 0 to minus infinity, that's it. So no need to find out another type of error. It is symmetric, that's why it will be similar. So you can find out also, no problem. So by using that symmetry relation, I am just writing, so the symmetry with respect to origin, I am writing probability that x lies in Z2 given 1 cent is also same. What is this probability of error? 0 is becoming 1. What is this error indicates? 1 is becoming 0, which means, so we are transmitting 0, but we are decoding it as 1 here. What about this? We are transmitting 1, but we are decoding as 0. So these are two types of errors are possible. Since this is symmetric, so the probability of this is same as probability of this. Okay. Now I am not doing any further calculations, I am writing directly. Now what is the final formula? Final formula is 1 by 2 of this probability plus this probability. Since these two are similar or same, so 1 by 2 will be cancelled out with one another. Now otherwise you can simply write this as 1 by 2 of this probability plus this probability. Both are same. So just you write only this probability. What is that? 1 by 2 ERFC root EB by N naught. 1 by 2 ERFC root EB by N naught. That is also similar to the Q of root 2 EB by N naught. Now this is the final probability of error of the BPSK. This is in the ERFC format, it is in the Q function format. You must remember in the both formats. So if you are getting any confusion, you remember in Q function format. You remember in only Q function format. You try to remember this relation between these two. You convert it into ERFC format. But so I cannot guarantee you that each and every time they will ask you either in the Q function format or in the complementary error function format. Okay. So they may use any one of these formats. So that's why you must remember this probability of error formulas both in the Q function way or in the ERFC function way. Okay. So this is what the final formula of the probability of error of your BPSK. What is that? Half of ERFC root of EB by N naught, that is also equal to Q of root 2 EB by N naught. Okay. Now with this we complete the probability of error of the BPSK. Now, so I explained the standard procedure. Okay. So I want to tell you the standard procedure, but there is a simplest way of finding the probability of error. How? Okay. Before that, so this is what the graph SNR versus bit error rate. Now this is how the probability of error curve would look like. This is a MATLAB simulation of probability of error of BPSK. So actually these are called waterfall curves. What are they called? Waterfall curves, because they are similar to waterfall. Okay. Now so this is a MATLAB simulation of probability of error of the BPSK. It is something like that. Now what is x-axis? SNR. What is y-axis? Bit error rate. So you remember, so the probability of error is also called as bit error rate. Now what is root EB? EB by N naught is also called as SNR. So please make a note of this. Generally, so EB by N naught is called as SNR. It is called as SNR. So the probability of error is also called as bit error rate. BER is also called as BER, stands for bit error rate. What does it mean? The rate of errors in the bit, which means if I say the bit error is 10 power minus 5, the bit error rate is 10 power minus 5. What do you mean by that? That equal to 10 power minus 5 means 1 by 10 power 5. Yes or not? Which means, so if you transmit 10 power 5 number of bits, only one is wrong. Among 10 power 5 number of bits, only one is wrong. That's the meaning of having a bit error rate. Okay. So the probability of error is also called as bit error rate. This EB by N naught is also called as SNR, signal to noise power ratio. Okay. Now this is a graph between EB by N naught versus probability of error. So it is similar to the waterfall nature. Okay. Now, so let me tell you another way of finding the probability of error. It is simplest way of finding the probability of error. Now, so instead of going with the constellation, I am just drawing the two conditional PDFs. What I am drawing? Two conditional PDFs. What are they? These two PDFs. Okay. So they are Gaussian PDFs. How the Gaussian curve will be? I told you already. This is a Gaussian curve. It's a bell-shaped curve. So the Gaussian curve will be like this. Correct? So what is this point? What is this point? It's a mean. Isn't it? So this is the Gaussian curve with a mean 0 actually. But so it is symmetric about mean. If its mean is 0, it is symmetric about 0. If its mean is not 0, it is symmetric about that particular mean. Okay. Now here, what is the mean of this fx of x given 1? S11. What is S11? Root EB. So the mean of the first PDF is root EB. So the mean of second PDF is S21 minus root EB. Okay. So if you draw these two PDFs, these two Gaussian PDFs, so the variance is same. What is the variance of each and every PDF? n0 by 2. Okay. So see, I explained all these things already. Because, so I told you, so the vector x is having n number of elements. What are they? x1, x2, so on, so on, xn. So we have found out the mean and variance of each and every element. I told you there itself. The variance is same for all the elements, that is n0 by 2. Okay. But the mean is different for different elements. What is the mean of each and every element? Sij. Okay. Now S11 is the mean of the first PDF, S21 is the mean of second PDF. S11 is root EB, S21 is minus root EB. Okay. So which means they are symmetric about EB and it is symmetric about minus root EB. So same thing is being drawn here. So this is first symbol with symmetric about root EB, is symmetric about minus root EB. So yeah, you just find out first symbol is 1, second symbol is 0. This is for symbol 1, it is for symbol 0. For symbol 0, the mean is S21. What is S21? Minus root EB. So for symbol 1, what is the mean? S11. What is that? Root EB. So this is the conditional PDF of symbol 1. This is a conditional PDF of x given symbol 1 is transmitted. So with mean root EB, that's why, so this Gaussian curve is symmetric about root EB. Similarly, this is symmetric about minus root EB. So these are two conditional PDFs of the BPSK modulation. Now where is the threshold? This is a threshold. Okay. Now, so actually what do you mean by conditional PDF? So if you take area under PDF, should get probability. Okay. Now what is this area indicates? So these two areas indicates probability of error. We have two areas. This area and this area. They indicates errors. The area under this curve is nothing but probability. It indicates probability of error. It also indicates probability of error. This colored ones. What do they represent? So what is happening here? So I have drawn the two PDFs directly. Okay, this is the threshold. Now actually, so this PDF belongs to which symbol? Symbol 0. Isn't it? So this PDF belongs to symbol 0, S0. But, so what is happening here? So it lies in which region? Z1 region. Which means, so what is this area indicates? It indicates that, so the probability that symbol 0 is transmitted, but you decode as symbol 1. This area indicates probability that you transmitted 0, but you are decoding as 1. Similarly, this area indicates your transmitted symbol is 1, but your decoding as 0. Because so they're crossing the threshold. You observe like this. These PDFs are crossing the thresholds. Okay. So this PDF belongs to symbol 0, but it lies in the region belongs to symbol 1. You decode wrongly. Okay. So that's why this area. What is this area? 0 to infinity area under this PDF. 0 to infinity this area. Please make a note of this. This area means 0 to infinity area under this PDF gives you one type of error. In the same way, this is another type of error. So since these two areas are equal, it is enough to find out only one area. So you just find out one area. Okay. Now this is the constellation. Okay. Now this is the threshold. Okay. Now this indicates one type of error. This area indicates another type of error. Okay. So here I have done simply by taking the conditional PDFs, nothing more than that. Okay. So these are two conditional PDFs problems. What is happening? The probability of error given 0 is transmitted is given by green region, which means so this area gives error when 0 is transmitted. Okay. In the same way, what is that area? So 0 to infinity fx of I have written r or x. You can write x also here, no problem. X given 0. 0 to infinity fx of x given 0 dx. So these things already we have found out just now. How much is that? Half of ERFC of root TB by n naught. Similarly, probability of error given 1 is transmitted. So you transmitted 1, but you are decoding as 0. What area? This area. This area indicates the probability of error when 1 is transmitted, but you are decoding as 0. Okay. So that is the blue region. This is the green region. It is also same. So the total probability of error is this much. I hope you are okay with this simplest method. Okay. So I will come again. I have drawn the two conditional PDFs which are symmetric about their means, root EB minus root EB. So this is threshold. So they are crossing the thresholds. Okay. Actually, this PDF should belong to symbol 0. But since it is crossing this 0 threshold, what do you decode? You decode as 1. So, but 0 is transmitted, you are decoding as 1. Then there is error. That is one way, one possibility. What may happen? Reverse may happen. So this PDF is crossing this side. It is crossing the negative side of the 0. Because this PDF belongs to symbol 1. But since it is crossing this negative side of the 0, you decode as 0. See, otherwise, let me tell you, this region is Z2 region, no? This region is Z2. This region is Z1. Okay? What is happening? So, the PDF corresponding to symbol 1 is lying inside the Z2 region. If anything lies in Z2, how you decode? You decode as 0. But actually what is transmitted? 1 is transmitted. So there is one type of error. But, so the probability of getting these two errors is similar, same. Because it is symmetric about 0. Everything is symmetric about 0. So that's why it is enough to find out only one area. So if we find out one area, this area also same as this area. So that's why I written very clearly here. Green area and blue area, they are same. You find out one area, it is exactly same as another area. So this is what the final probability of error. So you can write this answer in the exam also. This is also correct. So what I explained here is very standard procedure. This is a very standard procedure. It is true for any type of modulation scheme. But whereas this is only true for BPSK. Because it is one dimensional. We got only two conditional PDFs. So this is also correct. So you can write this also in the exam. So you will get 100% marks. So mostly in the GATE examinations, they will ask by drawing these PDFs only. So that's why you must know how to find out the probability of error by using these PDFs. Okay, so this is a way of finding the probability of error using PDFs. This is a way of finding the probability of error using Constellation. Okay, both are alright. You can use any one of them, but you must have idea of this type of calculations. Okay, now that is about the probability of error of BPSK. Now, so let us start the another type of scheme. Very briefly I will start here. So it is BPSK, means binary phase shift keying. Here what changes? The frequency of the carrier changes. So whenever there is a change in the state of the binary data, there will be a change in the frequency. Here the phase remains same, the amplitude also remains same. The only thing that is changes is, or that there is shift in the frequency. What is there? There is a shift in the frequency. So here also we are talking about binary, means we are transmitting two symbols. Obviously what are they? They are 1 and 0. Okay, so they differ by frequency, a fixed amount of frequency. They differ by a fixed amount of frequency. Now this is a standard form of the transmitted signals of the FSK. Now let me go to the standard procedure of BPSK. Now, so for symbol 1, you are transmitting S1 of t, that equal to root 2 EB by TB cos 2 pi f and t. Okay. For symbol 0, you are transmitting S2 of t, that is also equal to root 2 EB by TB cos 2 pi f2t. Now you compare S1 of t, S2 of t. They differ in only in frequency. They have same phase, same amplitude, they differ in the frequency. Here the frequency is f1, here the frequency is f2. Okay. Is it okay? So there is a shift in the frequency. Whenever there is a change in the state of the binary data, there will be a shift in the frequency of the carriers. Okay. Here frequency f1, here frequency f2, they are different. Okay. So that's why there is a shift in the frequency whenever there is a change in the state of the binary data. Okay. Now, so you can clearly observe m equal to 2. We are transmitting two energy signals. Okay. But what about n? N means the number of basis function. That depends upon the number of linearly independent signals. You observe very clearly, these two are independent of each other. You cannot write S1 of t in the form of S2 of t or vice versa. They are independent of each other. So that's why we need two basis functions. Here m equal to n. Because the given set of energy signals are independent of each other. They are linearly independent of each other. But in case of BPSK, what was happening? S1 of t equal to minus S2 of t. Only one is dependent, other one is independent. That's why there we got n equal to 1. We had only one basis function, but here the case is not like that. The given two signals are independent of each other. That's why we need two basis functions. What are they? Phi 1 of t equal to root 2 by TB cos 2 pi f and t. Phi 2 of t equal to root 2 by TB cos 2 pi f2t. These are the two basis functions we have. How we get these two basis functions? From the procedure. What procedure? Gram-Smith orthogonalization procedure. But here we don't need that rigorous procedure. We just write down directly. Okay. But so we know already the property of basis function. They should be orthonormal, which means they should have a unit energy and they should be orthogonal to each other. Now here, since we are having two basis function, we have to check the energy of each and every basis function. At the same time, you have to check whether these two are orthogonal to each other or not. So there was no problem of orthogonality in case of BPSK because we had only one basis function. Okay. Now here you try to check whether these two are orthogonal to each other or not. At the same time, are they having unit energy or not? Okay. Obviously, they will be having unit energies and they are orthogonal to each other. Furthermore, you have to choose these two frequencies such that these two are orthogonal to each other. That is your criteria. That is your duty. What your duty is to choose F1, F2 such that these two are orthogonal to each other. That's why, how to choose F1, F2? Fi equal to n plus I by Tb. F1 equal to n plus 1 by Tb. Okay, I think it's a mistake is there, maybe it is I, sorry, n plus I by tb. Okay, what is fn equal to? N plus 1 by tb. F2 equal to n plus 2 by tb. What is n? Any integer, you take any value for n, but fn equal to n plus 1 by tb, f2 equal to n plus 2 by tb. So if you choose f1 f2 like this, now these two will be orthogonal to each other. Okay, you try to write this properly. So there is a mistake, n plus I by tb. Okay, now so this is s1 of t, this is s2 of t. What is s1 of t? So for symbol 1, for symbol 0. Now you can observe very clearly how these two differ. They are having same frequency, sorry, they are having same amplitude and same phase, but they are having different frequencies. Okay, so how many cycles are there in a TB period? Over TB period, how many cycles are there? So 1 cycle and 2 cycle. There are only 2 cycles over TB period. Here how many? 1, 2, 3, 4. 4 cycles are there. Okay, so I have taken randomly. So the only thing you should maintain is they should have a different frequencies. Okay, so they have same amplitude and same phase, but they differ in the frequency. There is the shifting in the frequency of the transmitted signals. It is for symbol, let me take symbol 1, it is for symbol 0. So whenever there is a change in the symbol, there is a shift in the frequency of the transmitted signal. Okay, now what was happening in case of BPSK? There was a shift in the phase of the carrier. You go and check. So there was change in the shift, there is a shifting in the phase of the carrier. They were having same frequencies. So but there was a change in the or shift in the phase. Here there is a shift in the frequency of the carriers. Okay. Now this is a typical MATLAB simulation of the BPSK. So for symbol 0 this is a frequency. So but symbol 1 this is a frequency. Again symbol 0 this is a frequency. So whenever there is a shift in the, whenever there is a change in the state of the data, here 0 becoming 1, here 1 is becoming 0. Whenever there is a change in the state of the data, there is a shift in the frequency. Okay, so whenever 0 becomes 1, there is a shift in the frequency. Here whenever 1 becomes 0, there is a shift in the frequency. Okay, so the change in the data is represented with the shift in the frequency. Your frequency is less, your frequency is more, something like that. Okay, so the only thing is, remember, so they should have different frequencies. Okay, so either you can use more frequency for symbol 0, less frequency for symbol 1, or you can do reverse also. You can use less frequency for symbol 0, more frequency for symbol 1. Okay, you can use either of the one, but the only thing we should concentrate on is whenever there is a change in the state of the data, there should be a shift in the frequency. Shift can be low frequency to high frequency or high frequency to low frequency, doesn't matter. Only thing is we should be able to provide a shift in the frequency whenever there is a change in the data of the given stream. Now, so let us proceed a little further. Now here this is something like m equal to 2, n also equal to 2. Please make a note of this. Now things will be different now. In BPSK, what was happening? M equal to 2 but n equal to 1. So there was, the things were very, very simple because n was equal to 1 there, but here n equal to 2. Things will not be simple now. Now what is S1 of t now? How to write S1 of t? Phi 1 of t is root 2 by tb cos 2 pi fn t. So root 2 by tb cos 2 pi fn t. Now S1 of t equal to root eb phi 1 of t. I am writing S1 of t in the form of phi 1 of t. In the same way, what is S2 of t? So root 2 by tb cos 2 by f2 t, that equal to phi 2 of t. So what do you write? S2 of t equal to root eb phi 2 of t. I hope you appreciate this point. I hope it is very clear to you. You just try to write S1 of t, S2 of t in the form of phi 1 of t, phi 2 of t. Okay, you try to understand this on your own. Okay, so this is the simplest thing you can do. Now this is what for symbol 1 we are transmitting S1 of t, that is equal to root eb phi 1 of t. For symbol 0 we are transmitting S2 of t, that is equal to root eb phi 2 of t. Now S1 of t, S2 of t are linearly independent. That's why we need two basis function. Now but from the standard formula, what is S1 of t? S1151 of t plus S1252 of t. S2 of t equal to S2151 of t plus S2252 of t. Please just go and read the signal space analysis. Okay, it is very difficult for me to go to the signal space each and every time. It is not possible for me. Please, you read them properly. What is S1 of t? I have written there. S1151 of t plus S1252 of t plus S1353 of t plus S so on so on. Since n equal to 2, we had only two basis functions. So that's why I am writing S1 of t equal to S1151 of t plus S1252 of t. In the same way, S2 of t equal to S2151 of t plus S2252 of t. You compare these two with these two. What do you get? What is S11? Root EB. What is S12? 0. What is S21? 0. What is S22? Root EB. This is the comparison, by comparison. But what is signal vector S1? S11, S12, 2 cross 1. What is S11? Root EB. S12, 0. So root EB is 0, 2 cross 1. Now here S11 is a vector. Is a vector of order 2 cross 1. Here what is signal vector S2? S21, S22. S21 is 0, S22 is root EB. So 0, root EB, 2 cross 1. Here S11, S22 are two vectors of order 2 cross 1. Why 2 cross 1? It is n equal to 2. We got two signal vectors. Now what is the distance between these two signal vector D12? That is root of 2 EB. Okay. So I will try to write this later. Now this is the constellation of BPSK. Is it okay? Now what is the constellation? It is a two-dimensional signal space. Why two-dimensional? Because n equal to 2. Now phi 1, phi 2. I have drawn two axes, namely phi 1, phi 2. So I want to represent these two vectors on a two-dimensional signal space. Root EB 0. Where does it lie? Root EB 0 lie on the phi 1 axis. This is root EB 0. This is the first message point for symbol. First message point. This is the first signal vector S1. Okay, root EB. It lies on this axis, phi 1 axis. What is another signal vector? 0 root EB. Where does it lie? It lies exactly on the phi 2 axis. This is second message point. 0 root EB. Okay. Now this is the distance between these two signal vectors. How much is that? 2 times root EB. You just try to find out by using Pythagoras theorem. It forms a right angle triangle. So this is 0, this is root EB. 0 root EB. What is this will be? Square root of 2 EB. So the distance between these signal vectors, that is D12, that is norm S1 S2 equal to root of 2 EB. Okay. You just try to find out the distance between these two signal vectors, that is 2 times root of EB. Now, so next, so what we do generally? So if I go for just now, you remember this, it is a two-dimensional signal space having two axes phi 1, phi 2, and the two signal points 1 and 2, and the distance between these two is root of 2 EB. Okay. So anyway, we stop here. So thank you.